righty, we're going to talk about single-phase motors first. Okay? And so, list of different types of split-phase motors. Discuss the operation of split-phase motors. Reverse the direction of rotation of a split-phase motor, and discuss the operation of a shaded pole motor. Okay? We're going to discuss the operation of repulsion-type motors, single-phase synchronous motors, stepping motors, and universal motors. Split-phase motors. Split-phase motors classification: resistive start, induction run motor, the capacitive start, induction run, and the capacitive start, capacitive run. The most common one, and the one we have in the lab most often, is the capacitive start induction run motor. And we call that a PSC, a permanent split capacitive motor. Permanent split capacitive motor, PSC. And PSC means that it always has a capacitor, because it's this middle one, capacitor start. So what does that mean? If it's a capacitor start, well, we'll get to that in a minute. Split-phase motors use two separate windings to create the necessary rotating magnetic field. They're named the start winding and the run winding. And we just said this motor is capacitive start. So the capacitor is always connected to the start winding. Okay, that's something in the lab I'll ask you when you come up with a PSC motor. Start winding is more resistive than the run winding, which creates a phase shift between the start and the run winding. What does that mean? It's our phase shift is a shift in time, right? So if one's getting a magnetic pulse now and another one's getting a magnetic pulse a split second later, then it creates a direction of rotation, okay? And we always reverse the start winding, okay? The start winding is removed when the motor reaches 75% of its rated speed, assuming that it's a true start winding. A true start winding is one that has a, what kind of switch? Centrifugal switch, yes, a centrifugal switch, whatever you'd like to call it, centrifugal switch. And if it doesn't, then the run winding is always on. So it's not really a run winding, I mean a start winding. The run, did I say that correctly? Let me say it one more time. The run, if you don't have a centrifugal switch to cut out that start winding, then it's always running, right? And with our PSC motors, generally, we're not using the centrifugal switch, so it's always running. So it's not really a true run circuit, I mean a start circuit. Because to have a true start circuit, you have to have a centrifugal switch, because it gets cut out. So a lot of times we just leave it to circuit. Okay. Now this is going to come up again, so you need to remember this. Take a look at the start winding and the run winding. Its location and its size, and we talked about something else before, so you can identify them. Remember that? Okay. Resistive start, induction run motor. The start winding has much smaller wire. The start winding has much smaller wire. And where is it? Which one is closer? Now, you see this aluminum thing sticking up? That is your rotor. And right here we have the start winding. Now here we have the run winding. Okay. Go back a couple slides. I want you to take a good look at this. Start winding is more resistive. What makes it more resistive? It has higher resistance. Why? It's a little tiny winding and it's long. So it's got more resistance. It's a smaller winding and it's longer. And where is it? Near the out. What do we call the outside of the motor? The frame. Is it closer to the frame? Which one is closer to the frame? When you look at a motor in the lab, or the cutaway of the stator, look at, there's a big set of windings and a little set of windings. Look at which one's closer to the rotor. Make sure you understand this because I'm going to ask you in lab about 5 different times. Okay? So some of them use a resistive start induction run motor, and induction is just, you know, the windings. So this is where the different phase is created by running the current through a resistor before it goes to one of the windings. So in a resistive start, we might have at 40 degrees out of phase because of the resistance added before to the run winding or start winding before it starts. Capacitor start, induction run. Capacitor in series with the start winding creates a 90-degree phase shift between the start and the run winding. The start winding and the capacitor are removed when the motor reaches 75% of its rated speed. So if you wanted to know when does a centrifugal switch open, at about 75% of its rated speed. They're springs, and when the weights overcome the springs at a certain rotational speed, then that switch opens. Capacitive start induction run motor has more starting torque than that of resistive start, so it's a big advantage. So not most, but a lot of motors are capacitive start. Running characteristics are about the same. Direction of rotation may be changed by reversing the connection of either the start or the run. Once again, why do we change the start winding instead of the run winding? Same idea. Avoid excessive reluctance or avoid excessive residual magnetism. Here again, we have a capacitive start induction run motor. Look at the start winding, look at the run winding. Same setup as the other one, right? So they're built the same way. Here we have a drawing of the capacitive start, and here we have our centrifugal switch, which opens at 75% of the rotational speed. And here we have our picture of our applied voltage and our running voltage. Our start voltage and our run voltage. Okay, disconnecting the start winding when the motor reaches approximately 75%. We've already talked about that. Centrifugal switch, hot wire relay, current relay, or solid state starting relay. They're just different ways of doing that. So here we have, I believe this is a hot wire one. Yep, hot wire relay must be used to disconnect the start winding. So that's one way of doing it. Current relay, probably I'm not going to be asking you many questions about these in the lab because we don't have them. Okay? If we don't have them in the lab, they're not nearly as important to me because you're not going to bring one up, right? Okay, and here we have a solid state starting relay, and does the same thing. It just disconnects when a certain thing happens. Now, I do want to look at single phase motors and reversing them. We have now here we have to look at the winding termination numbers, okay? Because this is a dual voltage one, meaning they can run on 2 different voltages. All right? So we might put these windings in series or parallel. We're going to hook them in series for the higher voltage. We're going to hook them in parallel for the lower voltage. But also, how are we going to reverse this thing? We're going to reverse one set of these or the other, right? But we're going to, if they're hooked for the higher voltage, we're going to connect them in series. And we're still going to rotate. We're going to change the polarity of the current going to the start winding, not the run winding. Here we have a setup for what, high voltage? Yeah, high voltage connection. And you can see that the windings are connected in series. Same setup, except we're running them in parallel or shunt. The voltage motors with one start winding labeled T5 and T8. So occasionally you're going to have to look up winding terminations to see what you're looking at when you've got things sticking out, say for instance T5 and T8. If you're not sure, look it up. Okay. Dual voltage split phase motors, high voltage connection with one start winding. Only has one start winding. Dual voltage split phase motors. This is the low voltage connection with one start winding again. Okay. Get off track here. Okay, single phase motors, capacitor run motor. I think they mean capacitor start induction run, but okay. I don't see a capacitor on the run winding. This capacitor, I think capacitor start induction run, but capacitor start capacitor run motor with an additional starting capacitor. Okay. Now, shaded pole motors. We have shaded pole motors in the lab. Shaded pole motors are fractional horsepower. They only come in fractional horsepower. They don't come in large. They don't come in 1 horsepower. They only come in small motors. That's one disadvantage. A shaded pole motor works on the principle of a rotating magnetic field. One surprise, rotating magnetic field is created by shading coil wound on one side of each pole piece. The direction of rotation is towards the shading coil. Shading coil, if you look at the motor, it looks like it's just got 2 copper bands that's kind of clamped onto the windings, and that's what it is. That's all it is. Okay? And what happens to those copper circles that are clamped onto it? They get current induced to them. It runs around in a circle and creates a magnetic field. That's all it does. So what's the other disadvantage of a shaded pole motor? It will only run one way. It only goes one way. Fraction horsepower runs one way. And there's another disadvantage that you're going to have to find in your reading, because I'm going to ask you about that as we go. Okay. And here we're showing, now this shows a nice, cute little drawing here, but you know that this thing is actually just a little pair of copper bands clamped around the windings. So it's not something really complex here. We don't have, I don't think we have 4-pole shaded pole motors, but that's okay. That's just our lab. A repulsion motor, 3-phase attached repulsion motors. Repulsion motor, repulsion start, induction run, repulsion induction motor. Operates on the principle that like magnetic poles repel each other, highest starting torque of any single phase motor. So if you want to know which one has the highest starting torque, it is always a repulsion motor. Okay. Brushes placed at a 90-degree angle to the poles does not create any starting torque. But at 0 degrees, the pole does create a starting torque. What's the problem? And shifting the pole piece the other way will make it turn the other way. Okay. Repulsion start induction run motors. Short circulating ring short circuits the armature winding at approximately 75% of the stated speed, causing the motor to run as an induction motor. 2 types of repulsion start induction run motors, the brush lifting and the brush riding. Shows a shorting ring. And here we have a radial commutator used with a brush lifting type motor. We don't have one of those in the lab. I probably won't be asking you about that. So Don't get twisted about it. Repulsion start induction run motor. Look at this odd centrifugal switch. It's a weighted thing that overcomes the spring. Armature and scroll cage windings are both happening in a repulsion induction motor. Okay, single phase synchronous motors. What's a synchronous motor? It will operate at the synchronous speed. What is that? The synchronous speed is the speed of the rotating magnetic field. That is the synchronous speed. It uses a shaded pole stator to create a rotating magnetic field, small and develop only fractional horsepower. Use the path of least reluctance to maintain the synchronous speed. Two types of single-phase synchronous motors are the Warren and the Holtz. If you bring up a synchronous motor, and you might, if we have them in the lab, you might want to try and identify whether it's a Warren or a Holtz, because it will tell you how many, you can see how many poles it has, and that's the difference. Okay? So in your book, it'll tell you the difference between a Warren and a Holtz, and you might want to pay a little bit of attention to that. Oh, darn, it's going to give it the slide. That's okay. A Warren turns will run at 3,600 RPM because of the number of poles in it. Okay? Because of the number of poles it has. Now look at this. This has how many more poles? Scroll cage windings, it's got 6 of them, right? But this one, and the more poles, the slower the motor turns, right? So this one, a Holtz, only turns at 1,200 RPM. Can you identify one from the other? They look a little bit different, don't they? And those are actually, I know this is just a drawing, but that's not a bad picture of it. Okay. There's a stepping motor. They're used in computers mostly. Rotary is a permanent magnet, converts DC electric impulses to mechanical movement. Output shaft moves through a specific angular rotation each time the motor receives a pulse. So if you're trying to go to a certain place on a certain disk, then you give it a certain number of pulses as you go to that point. And if you can remember where that is by some magic, then you can get back there again. Rotor can be held in its position by applying DC power. Will operate as a 2-phase synchronous motor when connected to 2-phase AC power. Okay. Single-phase motors, a stepping motor is one of them. Magnetic lines with the average magnetic pole. The universal motor refers to as an AC series motor. May be operated on AC or DC. Creates high horsepower for its size and weight because of its high operating speed. Constructed similarly to a DC series motor by having wound armature and brushes. Okay, universal motor. Compensating winding is sometimes used, not always, to counteract the inductive reactance of the armature winding. Directions of rotation can be reversed by changing armature leads with respect to the field windings. Used in many power tools and household appliances. Armature and brushes of a universal motor. What are these right here? These things right up here. Segments of the commutator. Okay. Universal motor has an armature, series field, and sometimes a compensating winding, but not always. Effectively compensated universal motor. And then we're going to talk about everything we've learned. 3 types of split-phase motors. Most important one to us, the capacitive start inductive run, because that's what we have in the lab. Split-phase motors, we're going to refer to that motor as a PSC motor, permanent split capacitive motor. Direction rotation of the PSC motor is changed by reversing the connection of either the start or the run, but we don't do that. We change the start. When you come up and you have changed the run, it will be obvious that you did that. Rotating magnetic field in a shaded pole motor is created by placing shading coils. You know that. Repulsion motors, repulsion start, induction run, repulsion induction, and the two types of synchronous motors, the Warren and the Holtz, and stepping motors, which we probably won't play around with. Universal motors, you know, we will. Okay. Let's pause for a moment. All right. Now, the book has these in the opposite order, but I wanted to go over single-phase motors before we went into three-phase motors. You know that Tesla invented not only three-phase power, but three-phase motors, and everything about three-phase was invented by Tesla. And actually, the AC motor itself was basically invented by Tesla. And we're going to talk about a squirrel cage motor. We're going to look at why it's called that. Connection of dual voltage motors for proper operation on the desired voltage. Discuss the operation of consequent pole motors. We're going to talk about wound rotor motors, Selson motors, and maybe we will, maybe we won't. And the operation of synchronous motors, and determine the direction of rotation of a three-phase motor using a phase rotation meter. Power, three-phase power, will have one of two rotation schemes. You either call it ABC or BAC. ABC is, let's call that forward for a moment. Okay? Incoming power can have a rotational aspect to it. So if you hook up equipment that was hooked up to something that was connected to ABC, you take it off, you put it back on, and you connect it back BCA, it's going to run backwards, right? Well, there are worse things that can happen. There's a thing called a three-phase up system. I had a friend one time was putting in a computer center for the Navy, for their central payroll system. They're all of their computers, and they had an up system because if the utility power went down, they don't want their computers going off because it costs them about $1 million a minute to be off. Or maybe it's $1 million an hour. I think it's $1 million an hour. But anyway, so my friend Bob was working on this place, and he's taking the up system off. And he asked me to come over and give him a hand. And I said, Bob, don't you want to phase tape those wires that you're disconnecting from the up system? They are three-phase, you know. He goes, no, don't worry about it. No big deal. Well, about a week later, he blew up the up system, and he shut down the Navy's payroll system for about a week while he got a new up system and installed it and had his insurance company pay for everything. So phase rotation can be very, very, very important. A lot of times you don't want to have a motor run backwards, not even the first time, not even for a second. You've got to make sure that it turns the right way the first time, right? So because of that, you'll have to use a phase rotation meter. And you can find the phase rotation of the motor just by connecting to the meter and spinning it. Oh, what a concept. It's going to make electricity, right? The phase rotation meter will read the direction of the electricity, right? Ah, very clever. Okay. Back to motors convert three-phase AC into mechanical energy. They're smaller, lighter, and have higher efficiencies per horsepower than single-phase motors by almost 2/3, square root of 3. Almost twice, 1.7321, something like that. They're much more efficient. They're much better at doing what they do. And so they have become the most common motor in the world. It's this three-phase squirrel cage motor. Three-phase motors are extremely rugged and require minimum maintenance. These motors can be operated 24/7 for years without problem. Mr. Tesla patented the first induction motor as rotating transformers. Needless to say that if they were rotating transformers, they must have had windings in the field also. So they weren't exactly a squirrel cage motors. They were what's called a wound rotor motor. Okay, and we'll talk about that a little bit too. Three basic parts of three-phase motors: the squirrel cage induction motor, the wound rotor induction motor, and the synchronous motor. So there's a three-phase synchronous motor also. Okay, rotating magnetic field. The principle of operation of three-phase motor is that rotating magnetic field. The magnetic field rotation is caused by voltages that are 120 volts out of phase. We've talked about how three-phase power is created. Voltage periodic change, polarity, the arrangement of the stator windings. Okay, three-phase motors. Three-phase stators and three-phase voltage sine waves. We know that the power being created at 3 different times during a rotation, and that they're 120 degrees apart. Okay, magnetic field concentrated between poles A1 and A2. Magnetic field concentrated between poles of phase A and B. Okay, let's move right along. So how do we change rotation on a three-phase motor? It's got 3 windings. It's got 3 wires going into it. All you have to do is reverse any 2 connections. Change any 2. That's going to be the answer to a question that you're going to get asked at some point or another. You change any 2 connections. Okay, in three-phase there are synchronous motors. Rotational speed of the magnetic field determined by the number of stator poles per phase and the frequency of the applied voltage. And this is not just not individual stator poles, this is pairs of poles. So if we have 2 pairs of poles, it'll turn at 3,600 RPM all the way up to, you'll notice that it goes slower and slower the more poles there are. So a 4-pole motor will turn at 1,800. A 6-pole will turn at 1,200. A 8-pole will turn at 900. And this is the formula, and you're going to have to remember this. The speed of the synchronous motor, rotational speed, is 120 times the frequency divided by the pairs of poles. So if it's a 2-pole motor, that means it's got 2 pairs of poles. It's got 2 north and 2 south. Okay, so its speed is 120 times the frequency. And here in the United States, that'll be always 7,200 divided by the number of poles. So that makes it a little simpler, right? If we're talking about a European motor, it's going to be 120 times 50 divided by the number of poles. Okay, and we're going to do some work with that. You'll see that again soon. Okay, and three-phase motor phase rotation. Direction of rotation is either clockwise or counterclockwise. What a surprise! Reversing any two of the stator leads will reverse the direction of the rotation. Okay, a phase rotation meter can determine the direction of rotation before you start stuff up. Motor stator leads are often called T leads. T1, T2, T3. Right there we have phase rotation meter connected. See what's going to happen. You notice it's just connected to the motor. And so if we just spin the motor, it'll tell us what is going on here. Is this ABC or is it BAC? Okay. Then we can do it to the line and find out which way do we want this thing hooked up. Okay. Dual voltage motors. Many motors are designed to operate on 240 or 480. This type of motor has 2 windings for each. These are what are called 9-lead motors, and we're going to analyze in motor control lab how to figure out which leads are which just from looking at how the windings are connected. Okay, dual voltage motors. The other 3 leads are connected internally. There are 2 connected leads per winding. There are 2 windings per phase. There are 3 phases. Makes 12 connection leads. So this one we're talking about here is 9 leads. Of the 12 leads, 9 are usually brought out of the motor. So it's called a 9-lead motor. Okay, dual voltage motors. When motors connected to their higher rated voltage, the windings are going to be connected in series. When they're connected to their low voltage, they're going to be connected way we have the same voltage going across each winding every time, no matter what. Okay. T1 through 12 is standardized. Correct connection patterns are usually shown on the motor nameplate, and they look a lot like this. The ones we have in the lab are star motors, so they'll be laid out just like this. 7, 8, and 9 are already tied together internally. You can't see it, you can't do anything about it, but you can find them by finding that there are 3 leads coming out that are all connected together. That's 7, 8, and 9. Doesn't matter which one's which. We'll talk about that later. And then we're in the lab project where we do this, we're going to find these pairs because they are paired, they're connected. So we know that it's either 1, 4, or 3, 6. We just know they're pairs at first, right? But we can energize these windings and find out which ones get activated and which ones don't. And that's in the lab project, and you learn a great deal from that. You really need to do that project. High voltage connections, we're just going to connect the windings in series, sort of like this right here. Low voltage, we're going to connect them just like that, more or less. That's a delta. Do you know anything about it just yet? Some motors will have all 12 leads brought to the terminal box instead of the usual 9. These motors are intended for Y delta starting, and Y delta starting helps limit inrush starting current. We won't be talking about that in this semester. You will be talking about that in next semester. So the windings are all brought out, so you can hook it up delta or Y, or delta and then Y. Okay. Okay, scroll cage induction motors. Rotor contains bars, aluminum bars, and they're surrounded. Now you can't see the bars generally speaking. You cut off the end of them, you can see the aluminum bars sticking out. Why can't you see the aluminum bars? They're surrounded by iron plates. Why are they surrounded by iron plates? To increase the electromagnetic coupling between that bar and the winding that's energizing it. Because where is the current going in this motor, in that scroll cage bar? You're inducing current into an aluminum bar, right? Where does it go? That bar is actually square. It goes across, it goes down on each side, it goes across on the shaft. So the shaft is part of the circuit, and the current's going around in a circle. It's a short circuit. Why do we want to run current around in a short circuit like that? To create a magnetic field to interact with the other magnetic field. Okay? And this is what it actually looks like if you get the iron plates off of it. It's very hard to see that part. Take a look at the end of it. If we just cut a piece off, it'll look about like that. That's a cutaway view. 3 factors determine the amount of motor torque, strength of the stator magnetic fields, the strength of the rotor magnetic fields, the phase angle between the rotor and the stator. And in the synchronous motor, it's a 90-degree angle. Okay, slip. Every AC motor, except for a synchronous motor, has AC slip. All right? An induction motor never reaches synchronous speed. Slip is the difference between the synchronous speed and the motor speed. We looked at the synchronous speed before, right? 8-pole motor has 600 RPM, right? So if you see a motor, what was our 1800 RPM motor? Is that 2-pole or 4-pole? Very common motor, 4-pole. So if you found a motor and you energized it and it turned and you had a, what do they call it? Stroboscopic thing so that you could find the speed of the rotating motor. And you found that it was actually turning at about 3,500 RPM. Number 1, you know it's a 4-pole motor. Number 2, you can see how much slip it's got, right? Just from hooking it up and running it. Oh, what a good thing to know, right? Okay, the rotor has, okay, wound rotor induction motor. Wound rotor induction motor. And I believe that this is the one that Tesla invented. The motor is very popular in the industry because it's high starting torque and low starting current. Squirrel cage motor and wound rotor motor have similar stator windings. Stator winding out in the right inside the frame. Those are the windings in there, right? The rotor has wire windings instead of bars. This one has, so what is it turning inside there? Some windings, which are sort of like a transformer, right? Now, instead of having a commutator, thank you. Went blank completely for a second. Instead of having a commutator, we have slip rings to connect things inside this motor because we only need to have 3 connections. All right, so we don't need to make 22 different connections. Synchronous motor, the operating speed and the speed of the rotating magnetic field are the same. Operates at a constant speed from the load to full load. No load to full load. It's the only motor that will run at full speed with no load. And it will draw about the same current too. The motor can be used for power factor correction. What does that mean? We'll talk about that later. Synchronous motors sometimes can be used for power factor correction. So the squirrel cage bars known as the amortisseur windings are used to start the synchronous motor. A synchronous motor must never be started with DC current connected to the rotor, and a field discharge resistor is used to safety control excessive current and voltage. Okay. Field discharge resistors connected in parallel with the rotor winding during starting. Okay. Cells and motors, we're only going to talk about this very quickly. Used for position control and angular feedback information. Selson motors. More about Selson motors. Schematic. Different kinds of Selson motors. And then we're going to go into a review of everything we just talked about. You can read these a little later. They're all in your book. What are review pages? Alrighty. And that's everything we need to know about single-phase motors and 3-phase motors, I hope. If not, I don't know what to tell you.